Welcome to the 9th lecture of the 6th week of the machine learning course. This lecture will be about deep learning and its further developments. So the question I want to pose here is the following. Deep learning is a very hot topic at the moment. If you open any paper, look at TV and so on, it's a high probability that somebody mentioned this term. So what is it? And if I try to tell you what it is, will it be a climax or an anticlimax for you? The answer there, I would say, is that result-wise, it's a climax. Because what is normally referred to as deep learning today has produced more success stories than other parts of machine learning so far. However, from the purpose of this course, and rhetorically, it's an anticlimax, because we have this week already talked about almost everything that is of relevance for the concept of deep learning, in my opinion. So, for this final lecture on deep learning, it's not much more to add, because the constituents we have already covered. Even if I just told you that there is not much more to be said about deep learning than what we already covered this week, I like to give you a few facts about the timeline of artificial neural networks and deep learning, for that sake. Some of these facts have already been mentioned, but I have now collected them on one slide to give you my picture of how things has developed. So let's start from the beginning. So in 1959, Arthur Samuel coined the term machine learning. So since the beginning of artificial intelligence, machine learning has developed hand in hand with other sub-areas of artificial. It's been a very much integrated development. Also very early, there were pioneering work on artificial neural networks, as you have heard this week. For example, the perceptron. But artificial neural networks have always formed a kind of separate stream in artificial intelligence. So not always it's been a tight integration of the symbolic approaches in artificial and the artificial neural network. And this stream has been weaker or stronger depending on the time. It was very strong, like in the beginning, people were very optimistic. But then, as you see from the timeline here, it was a long break from 1990s, in the early 1960s to 1986. It's almost like it's like in the order of 25 years, where very little happened for various reasons. But in the mid-1980s, things happened. So on one hand, there were very important work by Rumelhart and Hinton, where they reintroduced multi-layer feed-forward networks and learning of those networks through backpropagation. And also, not much later, Rumelhart took the initiative to the precursors of recursive neural networks that then also developed hand in hand with artificial neural networks in general. And also not much later, from in the late 80s, there was the introduction of convolutional neural networks, in particular for image processing. So in the later half of the 80s, the key ingredients of deep learning, what is now called deep learning, was developed. A little ironically, at almost the same time, a researcher in machine learning, Rina Dechter, in one article introduced the term deep learning for multi-layered symbolic machine learning, not in the context of artificial neural networks. So at this point, people like Rumelhart rather introduced the term connectionist learning for his improvements of artificial neural networks. And published a well-known book with that title. So actually, it took a considerable time until in around 2000, the term deep learning started to be used for this combination of ANN, RNN, and CNN. by one researcher called Eisenberg and his colleagues. So around 2000, this terminology, in a way, was adopted by the ANN community. Of course, it's a good terminology, because if you have multiple layer networks and you have many layers, it's natural to call them deep. And as you have understood this week, especially recurrent neural networks has the effect that the number of layers grow, and that is also, of course, the case in the convolutional neural network approaches. So all these things tend to make the layers, the number of layers, larger. But then there is another development that is very important, because of course you may, in theory, create very powerful systems by creating systems with many layers, which was done through the combination ANN, RNN, CNN. Okay, but those complex networks also demands a lot of computational power. And that computational power was essentially not there at that point, in the beginning. So then, in the first decade of the 2000s, people started to experiment with using specialized hardware, GPUs, and we will come back to the use of these things in the coming week. So the application of those hardware made it possible to run these more huge networks in an efficient way. So these development happened in the first decade of the 20s, made this combination of ANN, RNN, CNN that we now, from now on, term deep learning, more useful. And an example of the usefulness happened actually in 2012, where one such system, actually a deep learning system in the sense of combining ANN, CNN, and RNN, made a great breakthrough in this ImageNet challenge that I described earlier this week with a system called AlexNet. So that was one of the first real success stories. And of course, the term deep learning has been adopted in the decade before. So with the breakthrough, also the use of this term spread. And actually today, 2019, the term deep learning is a dominating term for the work of artificial neural networks in machine learning. So this is my story to you. To convince you that the story I told you on the last slide is not just my invention, I now will point on a really good survey article, and I've given you the link. It's open access, so you can click on this link and you can find this article. And it's a review article from Nature, volume 521 in 2015. And this review article is written by three of the key researchers. So Geoffrey Hinton, you can call him, I would say, the still active key person in artificial neural network as such, and also more specifically in what's now called deep learning. Joshua Benju, who has really continued the work of Hinton and developed it further. John LeCun, who is a key person in the development of convolutional neural networks. So this is a kind of, what you find in this article is, I would say, the words from the horse mouth. It's not what anybody else imagined or suggested. It's the key person of this area who read this. Of course, the key person are not always objective totally, because these were the person who coined the term deep learning, so of course they want to promote it. But they are very serious researchers, being very instrumental in the development of the field, so if you should listen to anybody, you should listen to them, actually. So what you find on this slide is actually the quotation from the summary of that article, where they say the following. So they say that deep learning allows computational models that are composed of multiple processing layers, which is a rather trivial statement to start with, but with the important property to learn representation of data with multiple levels of abstraction. And this should be interpreted that these systems are able to themselves build up the representations, not only use pre-composed representations. They also say that these methods have dramatically improved the state of the art in speech recognition, visual object recognition, which are maybe the two very important test areas. Doesn't mean that these technologies cannot be used in other areas. It's just that these two has been at the focal point of the development of this area. But today, there are other things that are also important, drug discovery in genomics and so on, which are very important. So what deep learning does, it discovers integrated structure in large data set by using backpropagation algorithm to indicate how a machine should change its internal parameters that are used to compute representation in each layer from representation in pre. So that this little paragraph and in their summary, that really refers to the key machinery of feed-forward multiple layer neural networks with learning through backpropagation. So this is a key point here in what they think is deep learning. And then there is a final paragraph that articulates the two other components. So deep convolutional nets have brought about breakthroughs in processing images, video, speech, and audio, whereas recurrent networks have some light on sequential data such as text and speech, which were the two other components in the lectures this week. So, as a summary, to the right, you can see my own little graph on what constitutes deep learning. Is actually the combination of the basic machinery in feed-forward multiple-layer artificial neural networks, NN, with backpropagation, with the developments in convolutional neural networks and recurrent neural networks. So these are the triple of elements that constitutes this area. Summarizing my attempt to characterize deep learning, I give you my preferred terminology. So, computer science is a broad field, and it has a subfield called artificial intelligence. And artificial intelligence, in turn, has a subfield called machine learning. As part of machine learning, we have this combination of ANN, RNN, and CNN that we took some efforts to talk about this week. And this combination is what should be interpreted as deep learning. I also included the little bigger framework relating to machine learning. So actually, machine learning is today considered part of this umbrella concept, data science, which actually also cover other areas of computer science outside artificial intelligence, like big data, and actually also other areas outside computer science, and of course, centrally, statistics. So this is the big picture I want to convey to you. Finally, a few words then about the recent development in this area of deep learning. So, one important stream of research going on and development going on at the moment is going further on what was highlighted in this summary of the deep learning article I refer to, is the learning of structures and features in representation, the automated learning of structures and features. And this is like on the top of the traditional categories of machine learning. It's supervised learning, unsupervised learning, and feature learning. You can all do that without learning any new structures because you can predefine the structures and features. But the ambition here is to learn the structures and features themselves. So this seems to be still a very important endeavor in deep learning, not in all necessarily in all other parts of machine learning. So, but there is this inherent problem with ANN, is that it's at the bottom sub-symbolic, which means that if you create a very complex artificial neural network system and let it learn over a long time, you build up a lot of structures, and so far it's not been trivial to understand what is built up. You establish some knowledge in this system, and you can use the system for solving problems, and you can do that efficiently. However, it's not trivial to say actually what has been learned, what is the new knowledge created in the system that enables better performance. So, and of course people have realized that if we should use this in large scales, it's also important that not only creating more efficient systems with better performance, but also being able to, in a symbolic form, extract what has been learned in a way that we as humans can read it and understand it. So there are a lot of work, I would say, at the moment on that particular issue. So one of these new terms coming up is disentangled representations, which is not the whole story, but part of these attempts. The other things going on, because I hope you have noted that in my characterization of deep learning, associative memory didn't play a big role. So I talked about this combination of ANN, RNN, and CNN, which are the key of deep learning. Still, associative memory techniques is an important genre within neural networks as such, but obviously traditionally not what's been driven the development of deep learning. But today there are a number of attempts to actually integrate these areas. So integration of associative memory approaches with this mainstream of ANN, RNN, CNN techniques is an issue, key issue. And there are examples of that, something called deep belief networks as an example. Also, there are some work to connect the ANN, RNN, CNN technology to the learning of Bayesian system, Bayesian network related systems. There is also this terminology that we haven't really talked so much about, but there is this distinction in machine learning and related fields between generative and discriminative classification. So in discriminative classification, we start from the purely inductive approach. So we look at examples and we try to infer which abstractions or classes connect to the various examples we have. While in a generative approach, we actually start from our hypotheses or classes, and from that partly, I would say, through deductions, come up with probabilities for which kind of examples would belong to the classes. And of course it have to be validated by looking at the examples, but it's more of a top-down approach. Actually now there are more focus at the moment, I would say, on developing these generative approaches than the discriminatory ones, which were the classical. So also we can also see an enhanced use of the ANN, RNN, CNN, a bunch of techniques for the purpose of reinforcement learning. So I hope it's been clear that all work in artificial neural network is kind of orthogonal to these genres in machine learning: supervised, unsupervised, reinforced. I mean, this can be used for any of these. So it's not so that ANN is particularly useful in one of the shrines, can be used for all, depends on what you want. And there are more work going on now in using this technique for reinforcement learning. Another trend at the moment is scaling up of applications in time-critical and safety-critical applications like self-driving vehicles. Self-driving vehicles and similar things is a very, very hot technological area at the moment. And machine learning systems are needed in those contexts. But putting a machine learning system into such contexts expose you to issues like time criticality and safety criticality. And it's not evident that all the traditional machine learning services are ready to cope with those challenges. Also, we can see here a shift towards really being able to handle really big data. Traditionally, machine learning started with small data sets. I think for a long time they've been developing managing larger data sets, but still today we can see we have huge data sets. We have continuously generation of data from many sources. And if machine learning or deep learning should be able to be useful, it also have to extend its ability to handle these larger data sets. Also, of course, there is a continuous work on utilizing special hardware. This is here to stay. A self-driving car has a special GPU on board that can be used for machine learning. So things go on here, and new hardware architectures are tried, and this we will see for a long time be a development area. Finally, there is also a consolidation and enhanced open access to toolboxes and software support systems. For some time now, the support for an engineer that want to really apply deep learning has increased a lot. But there are still improvements to be made. And this is also active. So this is my summary of what's going on in this area. So by this, I will conclude this lecture, and I will conclude this week on artificial neural networks. So the only thing remaining is the last lecture, which has always been a tutorial on the assignments for this week. So thank you very much.